16th, 17th century, that's when Newton's laws are put into application, and we're looking at what's called classical physics. Why is it called classical physics, Jahir? Because it was classical music, right? 16th, 17th century. Classical physics. That's the course you're taking next year. Okay, you'll be taking classical physics. It's also called Newtonian physics because it's Newton's laws. And it's also called classical mechanics because what was our first model of the universe? That the universe is a machine. So that's why it's called classical mechanics. Classical, 16th, 17th century. Mechanics, because the universe is a machine. You will spend an entire year on classical mechanics. I'm going to give you a quick little explanation of some of the stuff you're going to learn next year. Okay? So, first of all, classical mechanics is deterministic, meaning there's one correct, exact answer. How long does it take for an apple to drop off the Empire State Building? 9.2 seconds, exactly. There's not maybe 8, maybe 12, exactly. You can calculate it. There are two categories: particles and waves. Next year, you will spend all your time talking about particles. If you take AP Physics 2, then you'll talk about waves. But next year, all particles. And anything that has matter is a particle. So, Michael, does this have matter? Okay, then it's a particle. Does my cup have matter? Then it's a particle. My voice.
No, I don't know.
Can you touch my voice? No. So then it's a wave. All particles are solid and composed of matter. All particles have a definite position in space and time. Luke, where's the tennis ball?
On a cup,
Does anybody disagree with him?
on a bottle,
I don't see it. I will take it on a mug.
on a bottle.
Yeah, we all know where it is. It's got a definite position. It was there at 1:55. It wasn't there at 1:54. There's a definite position in space and time. Particles cannot bend around corners. They only go in straight lines. Okay? Straight there, straight back.
A rubber band can bend around a corner.
Rubber band can't bend around a corner. Rubber band, if you shoot it, it's going to go in a straight path.
But if you like,
Now I know what you're thinking. Curveball. Okay? For every an object in motion stays in motion unless acted upon by an outside force. A baseball is not a perfect sphere. A baseball has seams. They're raised up. As the seams go through the air, depending on how you spin the seams, they'll cut through the air differently, creating a force on the ball. The force on the ball causes the ball to curve or move or drop. Okay? So, of course, if I throw this ball and someone's standing over there and they hit it, it's going to go around the corner because you just implied a force on it. Okay? But otherwise, particles travel in straight lines. They don't bend. Okay? And then the fourth, all right, Finn. I'm going to throw one of these at your head.
okay,
Okay? Choose carefully. Which one?
paper.
You chose poorly.
Why?
because you forgot to think about momentum. Momentum is the mass times the velocity. Mass in kilograms.
What's P?
P is momentum. And V is velocity in meters per second.
Why is momentum speed?
Because M was already taken. So, yes, the softball has more mass.
Wait, isn't velocity over second?
Whoops, yep, sorry, meters per second. Not seconds squared, just seconds.
What's M again?
Mass
Like what is on the board?
in kilograms. Mass is always in kilograms. So here's the reason why you don't want to be hit by this piece of paper. I neglected to tell you the velocity I'm throwing these at you. So the softball, I'm going to do this. That's not going to hurt, okay? But the piece of paper, I'm going to throw at 1,000,000 miles an hour. So it will go one side of your head and out the other because the momentum will be so great, okay? A car, if it's going slow enough, you could stop it. It doesn't have enough momentum. So keep that in mind.
Okay.
There are two types of momentum. Linear, which is a straight line. And that's the equation for it. P equals mv. The other type of momentum is angular, which is in a circle.
Oh,
Guess I
track,
can't do that.
travel.
So here's angular momentum. See, now you're going to be smart. Which is going to hurt more, this or that?
Probably that.
That, right? More momentum. Mass is the same, but the velocity is higher, okay? So I'm not going to write the equation down for angular momentum. It's a little bit more complicated. It's not horrible, but you will learn it in physics next year. You will have to know the unit circle. You will need to know radians, and you will need to know sine and cosine. So pay attention in your math class so that when you take physics next year, Jack, you'll know your radians and your sine and cosine. Okay?
I think Gavin's a question.
Got a question, Gavin?
AP Bio.
What's wrong with AP Bio?
So what if we take that instead?
You could do it. So you can go into the physical sciences, which is chemistry and physics, or you can go into the biological sciences, which is biology. There is less math in biology. There's a lot of math in chemistry and physics. You got to know calculus very well. You got time to get there. Like most of you will take calculus as a senior, okay? So you don't have to know calculus now. Biology, eventually you'll have to know some calculus. You won't have to have like super calculus, but some of the stuff that they do will be calc-based, okay? So pay attention to your math class. Waves. Waves are not solid, okay? They are pure energy. Waves are energy that flows through matter. By the way, this is the only page we're going to take notes on. Once we're done with page 3, we're done. No, for today. And then you'll get to work on your homework. So do not confuse the wave L with the medium through which it travels. So, for example, a sound wave. What does a sound wave travel through?
Here.
Air. Air is not sound,
Air's air.
but sound requires air to travel through. So if there's no air, Damari, there's no sound. What does a tidal wave travel through? Water.
Wait, so if you talked in space, nothing will come out?
Correct,
Because there's no air.
because there's no air. But you'd also be dead, because if you took up your space helmet to talk, it'd be too cold and you'd freeze.
Yeah.
Yes, Luke?
How do radio waves travel through space then?
So, we'll get to that, but I'm gonna answer it right now anyhow. A radio wave is a form of light. It's not sound.
Go away.
What does a seismic wave travel through?
Earthquakes.
Ground or earth? Can you have water without a tidal wave? Yeah, but can you have a tidal wave without water? No. So the wave is not the air, the water, or the earth. The wave is the energy traveling through that thing, okay? The earth is just nice and fine, and all of a sudden, energy travels through it. That's an earthquake, okay? Light.
That's just light.
Some of the stuff you're gonna learn in this unit is theory, we're not sure. So right now, Luke, as it stands, we believe that light is the only thing that can travel through nothingness, okay? So, radio waves are light, so they're able to travel through empty space. Did this class watch that video, What is Space?
Nope.
No? Okay, eventually you will. So, they used to think that light traveled through this thing called ether, but then they disproved it. But there are some scientists who still believe that light is traveling through something, but we haven't discovered it yet. Perhaps light is traveling through space itself. As we'll learn in the video, nothing, space is something. Space is not nothing.
Time. He's onto something.
Maybe it's traveling through time. So, who knows? Okay? There are 8 forms of light. Gamma, X-ray,
I thought gamma was an energy.
ultraviolet, visible, infrared, micro, radar, and radio.
We got those.
Write down those 8 forms of light.
What's the third one?
Ultraviolet.
What does it say after micro? Radar.
What's above micro?
Infrared. Unlike other waves, all light waves travel at the same speed. Every different note on the piano travels at a different speed because it's got a different frequency. But light waves all travel at the same speed, 3.00 times 10 to the 8th meters per second.
What's C?
C stands for celestial, which is a way of referring to the sun. or light. So c is the speed of light. So all waves of light travel at that speed. Now, you're wondering why I'm going to pound this into your head, because for the homework tonight, it's the starting point. You need to know, Kate, that all forms of light travel at that speed.
Wait, did that say C?
That says c. So, Serene, how fast do gamma rays travel? Gavin, I'm taking my son to get an x-ray tomorrow. How fast do the x-rays travel? I'm gonna go tanning later today. How fast do those ultraviolet lights in the tanning bed travel? How fast do you travel, Ben?
Speed of light,
Which is
3 times 10 to the 8 meters per second.
the lights in our room right now. Owen, how fast do they travel? That's visible light. Infrared, Andy, how fast does it travel?
3 times 10 to the 8th meters per second.
Okay, Ella, when you're making your dinner tonight in the microwave, how fast do those microwaves travel? And when I get, well, not me, but when Max gets pulled over later from the police using the radar, how fast do those radar waves travel?
3 times 10 to the 8.
And if you tune in your radio, or if you use your cell phone, Oliver, how fast do those radio waves travel?
3 times 10 to the 8.
Okay.
This is awesome.
Remember that for your homework, okay? That's the speed of light. All waves have an amplitude. And the amplitude is the height of the wave. Waves have to come in whole numbers. So the first fundamental wave. Second fundamental wave. Third fundamental wave. Amplitude.
Amplitude?
Amplitude.
What's the drawing showing?
The fundamental wave.
It's just showing the wave.
A light travel.
It'll make more sense when I demonstrate it. A node is where the amplitude is 0.
Is it A or N? Those are N's.
Those are n's.
Okay, that's what I had first.
N is the number of waves.
Waves per.
Wherever my amplitude is 0, that is called a node. Okay?
Oh, what is he doing? Wait.
That looks like a dip.
All right, so this is where this will make sense, okay, Jack?
It's going through the extra time.
First of all, don't confuse the medium with the wave. Is there a wave in this string right now?
That's bounce.
No. If I put energy into it, it's the energy is the wave. The string is not the wave. The energy going through the string. So the first fundamental wave. Where's the amplitude the highest, Mike?
In the middle.
In the middle. You're Mike. You look confused by that question.
I didn't hear what you said.
MJ.
Where is the amplitude 0?
No, it's MJ.
Reach out. Hand and the doorknob.
Yeah.
Why is it
and
MJ?
and
That's
doorknob.
what Gail calls it.
So those are nodes, Ariana, where the amplitude is 0. First fundamental
Gail calls
wave.
you MJ.
You can't have half a wave. So when I go from 1 to 2, it goes into chaos. And out of chaos will emerge the second fundamental wave. Okay? Chaos. Now, how many amplitudes?
2.
How many nodes?
3.
3, right?
No way he can do any equals 3. Yeah, how are you do any equals 3? Oh. Yo, that's like any equals 5. Yeah, I don't see it. I'm not gonna lie. I see
It's
it.
hard to do.
I don't see it.
Whoa!
I saw it for a second. Okay.
So
Wait,
you
that
can
was
only
more,
have
there's
whole
3
numbers
and
for
4.
waves.
Yeah, it was like 5. That was like n equals 5.
Might have been. You keep going. N equals 5, 6, 7, 8, 9, 10. Okay? I'm going to put number 4 up here. All waves have a wavelength. It's the distance between the two peaks, or the distance between the two troughs. And the symbol we're going to use is lambda.
Ooh.
Lambda is the wavelength. And must always be in meters.
Oh, God, it's not me.
What is that?
Lambda must be in meters. And as I referenced before, a lot of times we're going to deal in angstroms.
That is not.
1 times 10 to the 10th angstroms is equal to 1 meter. Okay? So on the homework, you're going to have to convert from angstroms to meters first. Wavelength.
What's an
It's
angstrom?
It's a Swedish word, it just means small unit of distance.
So the angstroms are the tip? Or like the...
An angstrom is like a centimeter or a meter, it's just a really small unit of distance.
So what are the purple arrows?
From top to top, that's your wavelength. Or bottom to bottom, that's your wavelength. Good question, Ben. Yep.
So for that thing that you drew right there, that
This
would
one?
have 5 nodes, right?
This would have 1, 2, 3, 4, 5
Alright,
nodes.
yeah.
All right. Frequency. All waves have a frequency. So this would be low frequency. This would be high frequency. Notice that the amplitude will be the same. So the amplitude's not going to change, the frequency is. So the height of the waves is the same, it's just that I've got more waves. And F is going to stand for frequency. Any questions so far before we start kind of doing a little bit
So
of math?
what changes, like the amount of energy in the wave? Like if it's same height, but there's more, it's higher frequency.
It depends whether it's a sound wave or a light wave. So frequency
I know.
is the number of waves per time. Usually we use the letter F. Some books use the Greek letter nu. Okay? So I switch between the two, so you're exposed to both of them. F or the Greek letter nu stands for frequency. The textbook uses nu. Bless you. So, over the summer, I went down to the beach, and as I usually do, I took a stopwatch, and I counted the number of waves that hit me. And there were 10 waves hitting me every 2 seconds.
Wow.
No way. You're fucking die.
So 10 waves hit me every 2 seconds.
You're gonna drown.
Mike, that's not drunk.
You could be actually.
So my frequency would be 5 waves per second. That's not a speed. Okay, that's just telling me how many waves are hitting me. It's not telling me how fast the waves are going. Okay? Now science does something that I don't like. You don't write the word waves when you're talking about frequency. You just write 5, and then the seconds, is that in the numerator or the denominator?
Denominator.
Denominator. So you'd write 1 over seconds. Now in math class, what do you call something that it's 1 over? Yeah, it's a fraction. But this is where, like, sometimes paying attention to math vocabulary
Decimal.
is important. This is called the inverse, or it's also called the reciprocal. So remember those 2 words, because they will typically write frequency as this. Seconds to the negative first. It's called a reciprocal second. It's no different than saying x to the negative first. It means 1 over x. 5 reciprocal seconds. What does it really mean? It means 5 waves per second. So 5 inverse seconds, 5 reciprocal seconds, because seconds is in the denominator. Okay? What's 1 over x? X to the negative first. What's 1 over seconds? Seconds to the negative first.
Okay.
This is math. Right? Is the math not mathing?
What do we do with that though?
You should always be putting units. Okay? I just want you to know what frequency was really telling you. Okay? And then, last but not least, 1 hertz is 1 reciprocal second. So I could put this then into hertz, 5 hertz. So all of these mean the same thing. 5 waves per second, 5 1 over seconds, 5 inverse seconds, or 5 hertz. They all mean the same thing. Textbooks are not very explicit about that. Frequency is not the speed of the wave, okay? How do you calculate the speed of a wave? Well, speed is equal to distance divided by time, right?
Yes.
Is S speed?
S is speed. So how far did my wave travel? And in what time? So my wave is here. What distance did that wave just travel? It traveled from there to there. What is that distance? So how do I figure out that purple distance here from one side to the other? Well, by definition, the wavelength is the length of the wave. So how many waves do I have here? 1, 2, 3. 3 waves, and I know its wavelength. So the distance would be equal to the number of waves times the wavelength divided by the time.
So, number of waves.
Number of waves times the wavelength divided by the time will give you the speed of the wave.
Times. What's that little stick thing again?
Wavelength.
Wavelength. Now in this equation here, and I wrote it this way for a reason. What's another name for the number of waves divided by time?
S equals D divided by T.
Yeah, but the waves divided by the time is the frequency. So we're going to substitute in. So the speed of my wave is now equal to the frequency times the wavelength. This equation is good for any wave. Sound wave, water wave, seismic wave. It's the frequency times the wavelength gives you the speed. Okay? Frequency is not the speed of the wave. Now light, we said, was special. Light always travels at the same speed. So we're going to modify this equation for light.
How many frequencies are in that thing?
This one,
Yeah.
I don't have a unit of time up there, so I can't tell you.
Jitterbug.
So this is the equation we're going to use, okay, Jack? Because we're going to deal with light. When you take AP Physics 2, you're going to use the top equation because you're going to be dealing with sound waves. So C equals F lambda. We're going to do one example problem, and then you're going to work on your homework. Okay? So, I guess I ran out of space. C is the speed of light. What is the frequency if the wavelength is 780 nanometers? If you ran out of space, just put it on the next page. You can put it on the next page. We're not going to use all the next page. So what is the frequency if my wavelength is 780 nanometers?
Yeah.
So what should I do? Just start plug numbers in and see what happens? No. That's how you get the wrong answer. What are we trying to find? Frequency. What's my wavelength? Nanometers. Speed of light. And then I've got my equation. Always write your info. Write your equation. Don't just start plugging numbers in. When you just plug numbers in, that's when you get things wrong. Because when you look at these things, what's the wavelength in? Nanometers. What's the speed in? Meters. That's a problem. That's why wavelength must always be in meters. That's why we practiced conversion before we did the physics. 1 times 10 to the 9th nanometers is 1 meter. That equals 7.80 times 10 to the negative 7th meters. So now my wavelength is good. My speed of light is good. Do we plug numbers in now?
Yeah.
No, algebra. Then plug. C over lambda equals F.
Alright.
Now we can plug the numbers in. I think this is the hardest you conceptually, yes.
Is that negative 7?
Yep.
Yeah, just, what? Can you tell me what the bottom one is?
Meters.
No. Like, what is it? Is it 7.8?
7.80 times 10 negative 7. Now, L, don't just write down what the calculator tells you. Think about it, okay? So, 10 to the 8th divided by 10 to the negative 7. What should that be approximately? What do you do when you divide exponents? Subtract. So, Jack, 8 minus a negative 7 is what? Your answer should be approximately to the 15th power. Maybe the 14th, maybe the 16th. So you should know whether or not your answer is somewhat reasonable. If you end up with 10 to the 4th, you did something wrong, okay? If you put this into your calculator, you will get 3.85 times 10 to the 14th. What are your units? Meters cancels with meters.
Seconds.
Where is your seconds? Is it in the numerator or the denominator of that fraction? Denominator. So your units are not seconds, but 1 over seconds, which is usually reported as inverse seconds, okay? Inverse seconds and seconds are not the same thing. Inverse means it's in the, almost done. Let's convert that to megahertz. One inverse second is 1 hertz. 1 times 10 to the 6th hertz is 1 megahertz. So then that is 3.85 times 10 to the 8th megahertz.
I fill up my water.
In like 1 minute. So your homework will ask you to do it in inverse seconds, they'll ask you to do it in hertz, they'll ask you to do it in megahertz. Okay? What questions do you have?
Now can I go?
Yeah. Just 1 second. Are there any other questions? You only have 4 problems, okay?
What page is that homework on?
I'll tell you in 1 second. There are no questions?